Poisson brackets. Poisson brackets. So let us consider the functions capital F and G. When these two functions depend upon the position coordinates qk and momentum coordinate pk and time t, Poisson brackets of f comma d g can be defined as brackets f comma g subscript here q comma p, which is equals to sigma k equals to 1 to n dou f by dou qk dou g by dou pk minus dou f by dou pk dou g by dou qk. So we can express, because here f comma g, these are the two functions depend upon these position and momentum coordinates. So we can express like this. So for the brevity, we may drop these subscripts and can write the position bracket as f comma g. And we know that f equals to small q, capital P, comma t. So here f is a function of q, p, and t. So the total time derivative of the function f can be written as, so df by dt we can write. So here f is a function of q comma p comma t. So by using this one, we can write the total time derivative of function f can be written as df by dt equals to, so here df by dt, because it is a function of t, plus sigma k equals to 1 to n dou f by dou qk dot plus dou f by dou pk dot. Here f is a function of qk and f is a function of pk. Here we have expressed. So by using the Hamilton's equations, we have q dot k equals to dou h by dou pk and p dot k equals to, we have dou h by dou qk. So these are the Hamilton's equations. So if we replace these Hamilton's equations in this equation number 2, so df by dt we can write as f dot, which is equals to dou f by dou t plus sigma k equals to 1 to n dou f by dou qk. So q dot k we are replacing with dou h by dou pk minus dou f by dou pk. So here p dot k is minus p dot k equals to dou h by dou qk. So we are placing here minus in the place of here. So dou f by dou pk dou h by dou qk. So this is equation number 3. So in the view of the definition of Poisson brackets, which is given by equation number 1, already we have seen. So here this is a Poisson bracket, how we can express. So by using in the view of that equation number 1, so here df by dt equals to dou f by dou t plus, so here if we observe, it is in the form of Poisson bracket f comma h. So dou f by dou t plus f comma h. This is equation number 4, because here we have seen in the view of equation number 1 like this, and here we have f comma g subscript here q comma p, but here we have replaced g with h. So here we have considered h. That means we have make this equation by using Hamilton's equations. So in the place of q, we have write this Hamilton's equation. So here in the view of Poisson bracket, which is given in equation number 1, df by dt equals to dou f by dou t plus f comma h, which is the equation number 4. So from this equation, we see that function f is constant of motion if df by dt equals to 0 or dou f by dou t plus f comma h equals to 0. Either it may be 0 or this may be 0, so that the function f is constant of motion if this 0 or this will become 0. Now, if the function f does not depend on time, so if function f does not depend on time explicitly, so what will happen? Dou f by dou t equals to 0. Then the condition for f to be constant of motion is obtained to be f comma h equals to 0. So thus, if the function f does not depend on time explicitly and is a constant of motion, its position bracket with the Hamiltonian vanishes. So in other words, a function whose position bracket with the Hamiltonian vanishes is a constant of motion. So this result does not depend whether h itself is a constant of motion. Now let us see the equation of motion in Poisson bracket form. So here now we will consider the special cases of equation number 4. So here we have equation number 4. Let us consider some special cases of equation number 4. So we have df by dt equals to dou f by dou t plus f comma h, which is in the equation number 4. Now let us replace f with small qk. If you replace f with small qk, what will happen? So dqk by dt equals to dou qk by dou t plus, in the place of f, we are replacing with qk comma h. So let us see here, if f does not depend on time, that means dou f by dou t becomes 0. So partial derivative becomes 0. Now here if we see, if f does not depend on time, so partial derivative becomes 0, but not this actual derivative. So then what will happen? Dou qk by dou t equals to 0, dou pk by dou t becomes 0. So because of constant of motion. So here in the place of f, we have replaced with qk. So dqk by dt equals to dou qk by dou t plus qk comma h. So dou qk by dou t 0, because of constant of motion, this becomes 0. So dqk by dt we can write as qk dot, which is equals to qk comma h. Now if we replace f with small pk, if we replace f with a small pk from here already we have replaced with qk. Now if we replace with pk, we will obtain dpk by dt equals to dpk by dou pk by dou t plus pk comma h. So here, because of constant of motion, dou pk by dou t equals to 0. So this becomes 0. So this one we can write as p dot k equals to pk comma h. If you replace f with h, we will obtain in equation number 4 dh by dt equals to dou h by dou t plus h comma h. So h comma h equals to 0. So h dot equals to dou h by dou t. So these equations 7a, 7b, 7c are identical to the Hamilton's equation a, b, c, d of already which we have studied. So q dot k equals to dou h by dou pk, p dot k equals to minus p dot k equals to dou h by dou qk, minus dou l by dou t equals to dou h by dou t, dh by dt equals to dou h by dou t equals to minus dou L by dou T. So these equations 7a, 7b, 7c, these are identical with these equations as the equation of motion in Poisson bracket form. Now let us discuss the properties of Poisson brackets and fundamental Poisson brackets. So the Poisson brackets has a property of antisymmetry, which is given as f comma g equals to minus g comma f. So here Poisson bracket has a property of antisymmetry, f comma g equals to minus g comma f. Because f comma g, we can write sigma k dou f by dou qk dou g by dou pk minus dou f by dou pk dou g by dou qk, which is equals to, if you write in minus g comma f, so minus dou g by, we are replacing g and f here, minus dou g by dou qk dou f by dou pk minus dou g by dou pk into dou f by dou qk, which is equals to minus g comma f. So thus Poisson bracket does not obey the commutative law of algebra. So as an application of the Poisson brackets, we are giving below some of the special cases. Here this is the Poisson bracket, f comma g equals to sigma k dou f by dou qk dou g by dou pk minus dou f by dou pk into dou g by dou qk. So when g equals to ql, that means here g depends on ql. When g, if we replace g with ql, what will happen? F comma ql equals to sigma k dou f by dou qk. We are replacing g with ql. So dou ql by dou pk minus dou f by dou pk dou qk by dou ql by dou qk. So here on differentiating, here dou qk by dou ql by dou pk. So here this becomes 0 on differentiating dou, that means here dou ql by dou pk becomes 0, dou pl becomes 0. So this term becomes 0. So we will obtain f comma ql equals to minus sigma k dou f by dou pk into dou ql by dou qk. Because here q does not depend on p, so this becomes 0. So f comma ql equals to minus sigma k dou f by dou pk into, so here dou ql by dou qk we can written as delta lk. If L equals to K, delta L becomes 1. So here, if we can write this one as delta LK. If L equals to K, this becomes 1. So F comma QL equals to minus 2F by dou PL, dou PK into 1. So this is the equation number 9. Now, if we replace F with QK in equation number 9, So if f equals to qk, if you replace f is qk in equation number 9, we'll obtain qk comma ql equals to f means here qk, so minus dou qk by dou pl. So on differentiating, this becomes 0. So qk comma ql equals to 0. So if f equals to pl, if we substitute f equals to pl, so here pl comma ql equals to, so dou f means here pl, so dou minus dou pl by pl, which is we can write as minus dou kl, which is equals to, we write dou pl by dou pl, so we can write as dou delta kl or 1. So pk comma ql equals to minus dou pk by dou pl or minus delta kl. We can write like this. So when g equals to pl, if we replace g with pl, we'll obtain, actually this is the Poisson bracket, f comma g equals to sigma, this is the sigma k dou f by dou qk dou g by dou pk minus dou f by dou pk into dou g by dou qk. This is the Poisson bracket. So if we are replacing g with pl, so f comma pl equals to sigma k dou f by dou qk, g place, so here we are replacing pl in the place of g, dou pl by dou pk minus dou f by dou pk dou pl by dou qk. So here dou pl by dou pk, which is delta ql, so dou pl by dou qk becomes 0. So this term becomes 0. So here we will obtain, this is delta lk. So f comma pl equals to sigma k dou f by dou qk delta lk. If L equals to K, this becomes 1. So F comma PL equals to sigma K dou F by dou QK. If you substitute, if you replace F with PK, we will obtain PK comma PL equals to dou PL by dou QL, which is equals to 0. For F equals to QK, we will obtain QK comma PL equals to dou QK by dou QL, which is equals to delta KL. So this one, delta KL. So the above results can be summarized as follows. So already we have shown these results. So QK comma QL equals to PK comma PL equals to 0, and QK comma PL equals to delta KL. From these are from equation number 13 and 10, and this is equation from 14. So this one, QK comma PL equals to delta KL, and these are from 13 and 14 equations. 13, 14 from these two equations. Here QK comma QL equals to PK comma PL equals to 0. So where here delta KL, it is the Kronecker delta symbol with the property delta KL equals to 0 for K not equals to L, and delta KL equals to 1 for K equals to L. So equation 15 and 16, these are called fundamental Poisson brackets. Thank you, children.